Hey everybody, welcome to Math 35. This is college algebra at College of the Sequoias. This is fall of 2020 and I'm filming our fifth lecture. It's considered a review lecture. It's from introductory algebra. And this section is R5. So section R5, and it is on rational expressions. Now, rational expressions has the word ratio in it. And recall, ratio means fraction, or yields a fraction. So we're going to have algebraic expressions that are fractional, that are ratios. And this means we're going to have, what that means in terms of what we know, we'll have polynomials, P and Q, such that we'll have P over Q. So we'll have a polynomial on top, polynomial on bottom. It's important to note this can lead some problems. Recall, fractions cannot have denominators equal to 0. Equal to 0. Which means every value that does not make the denominator 0, or the bottom, it's quicker to write than denominator, equals 0, is a valid input. And so that leads us to our next term. The domain of a polynomial is all valid inputs, which means the domain of a rational expression includes all inputs that do not make the bottom 0. Equals 0. One thing that they call these domain violations. It violates the domain if it equals 0. And you'll hear me use, Jones uses the phrase bad juju. Bad juju. So if a number causes the fraction to break, shall we say, or make the denominator equal 0, it's a bad juju number. So let's take a look at some examples. You should pause this, write more if you need it. So, well, simple examples of rational expressions include things like, well, we could have something like x minus 7 over x plus 3. We could have something like, well, let's add to that. Let's make that x minus 7 over x plus 3, and let's multiply it by x minus 1 over x minus 1. And this one, we could have something like 2p squared plus 7p minus 4 over 5p squared plus 20p. And we can take a look at anywhere that this violates the domain. So let's call this one A, this one B, this one C. So for A, what violates the domain is our question. Set the denominator equal to 0. Equal to 0 and solve for the variable. And we'll do that on all of them. So maybe I'll move the A down here. Say this one, A down here. So the denominator is x plus c. We're going to set it equal to 0. We know how to solve algebraic equations. We'll isolate x. We're going to subtract 3 from both sides. And we get x equals -3. That violates the domain. So the domain is all real numbers except x equals -3. And they like to do that, say stuff like this, where like in that set builder notation, all values x such that x is in R, x does not equal -3. That's a long, tedious way of doing, just saying, it's easier just to say domain x cannot equal -3 and good to go. Most people are satisfied with something like that. This is the math jargon. If we take a look at B, over x plus 3, x minus 1. Well, the denominator is x plus 3 times x minus 1, 0. This is where we use that 0 property rule. If two numbers multiply to make a 0, and that's what this is doing, a times b equals 0, one of them has to equal 0, or both. But since they can't, x can't be two different numbers simultaneously, we just take these and set each of these equal to 0. And we do the same thing. We solve for x, we subtract 3 from both sides, we add 1 to both sides, and x cannot equal -3 or 1. That's the domain. X cannot equal those, or domain is everything else. And I want you to note that this is true, even though we can cancel out x minus 1 on top and bottom. And I'll pause, let you finish writing it down. Okay. And the reason why, I could put it on this, add more to it. We got x minus 7 times x minus 1 over x plus 3 times x minus 1. I can write that as two fractions times x minus 1 over x minus 1. But any number divided by itself, a number divided by itself equals 1. So this whole thing simplifies to x minus 7, x plus 3. But since we started with this one, but we started with the x minus 1 in there, so it still violates the domain. Okay? And this is based on what we just did there is really the fundamental theorem of fractions. If we have a times c over b times c, this equals a over b times c over c. And c's divided by c equals 1, which means this equals 1. And if we remove the dot in there, AC over BC equals A over B. C cannot equal 0. B cannot equal 0, of course. Both of those would break the equation. So let's take a look at some examples of how we would apply this. First example we'll do. 12x squared minus 30x over 4x squared minus 25. And we're going to factor top and bottom separately. Which means you're going to get a lot of practice from the last section. I hope you mastered section R4. If you didn't, this section is going to take you a lot longer, or you'll get a lot of practice doing this section, and that will help you master R4 that way. So we look at the top one. 12 and 30 are both divisible by 6, and x squared and x are both divisible by 6x. And if we divide 12 by 6, we get 2. We divide x squared by x, we get x. And then if we divide 30x by 6x, we get 5, and there was a minus sign in there. This one right here is really 2x squared minus 5 squared. So our difference of squares pops up. And remember, that was, we do a minus b, which is 2x minus 5, times a plus b, 2x plus 5. A squared minus b squared equals a minus b, a plus b. So, domain violations. Two x minus 5 equals 0, or 2x plus 5 equals 0. And we get x equals 5 over 2, or x equals negative 5 over 2. And these are commonly written as one thing. We say x equals plus or minus 5 over 2. So that's a way of simplifying this whole thing right here, writing it in less stuff. And that's what violates the domain. So we're going to say x cannot equal plus or minus 5 over 2. Then we'll cancel out things that appear on top and bottom. And we're left with 6x over 2x plus 5. Okay. To cancel stuff from top and bottom, or terms from top and bottom. All terms on top and bottom have to be multiplied together. They cannot be separated by addition. Addition or subtraction. This is a reminder. I hope you know that. I'm going to go back to the very first example we had. We had x, what was it, x minus 7 over x plus 3. You can't cross off the x's. This does not equal negative 7 over 3. Even when you cancel, it replaces it with a 1. It does not equal 1 minus 7 over 1 plus 3 unless x equals 1. And I can give you an example that this doesn't hold true. If x equals 10, x minus 7 over x plus 3 equals 10 minus 7 over 10 plus 3, which is 3 over 13. That's not negative 7/3. So you can't cancel terms combined by addition or subtraction. Okay? I do want you to recognize when we had this, let me get to the other page. Let me do this one I had here. The 6x times 2x minus 5 and then 2x minus 5 times 2x plus 5. There are minus signs and plus signs in them, but they're inside of a giant thing. If I had replaced this with like a y, then the y is multiplied by the 6x and the y is multiplied by the 2x plus 5. So that these things are multiplying the 6x. They're not added to the 6x. This 2x minus 5 is multiplied times the 2x plus 5. It's not added or subtracted to it. And that's what I mean by that. I really wanted to emphasize that. I took a whole page to do it because students, it's a common mistake. And it's very frustrating. People get confused by the difference between it. Multiplication we can cancel, addition or subtraction we cannot. Okay. So let's look at some more things. Let's do some more examples. Let's do x squared minus 8x plus 16 over 8x minus 2x squared. I want you to pause the video for a second, or as long as it takes. Try to factor the top and bottom. Get some practice in. You are not going to do well in this class if you don't practice it. Doesn't matter how much I tell you. If you don't do this yourself, you're going to fail. So practice, practice, practice. Pause these videos when I recommend it and try to do this yourself. Okay? Taking a gulp. Should have given you time to pause, work it out, and unpause it to come back. The top factors into x minus 4 times x minus 4. Or you could put x minus 4 squared. The bottom, we can pull out a 2x, and we're left with 4 minus x. Okay? Now, these are pretty close. I got x minus 4 and 4 minus x. Notice this is where this is why we can do it. If I have that, I'm going to recopy that line down. And I multiply this by -1 over -1. So multiply by -1 over -1. And then what we're going to do is multiply the -1 into one of the terms in parentheses. Just do one of them. So I'll do the bottom one. I'm going to leave the -1 out front. And then I've got times x minus 4 over x minus 4. I've got 2x down here. But if I multiply the bottom by that, the -1 times the 4 minus x, it just changes the signs. And now I've got -4 plus x. Remember the commutative property of addition. I can switch the order of these. This becomes x plus -4 or x minus 4. And now I can cancel them out. So I'll rewrite that before I cancel. I've got -1 times x minus 4 over times x minus 4 all over 2x times x minus 4. Now the x minus 4s cancel. And we don't even need the 1 anymore. We can leave it as negative x minus 4 over 2x. I recommend putting the x minus 4 on top in parentheses just to make it clear that the negative applies to both if you put it up there. And that's what that simplifies to. Our domain violations, the domain violators, we set 2x times 4 minus x equal to 0. This is one term, and that is another. 2x equals 0, or 4 minus x equals 0. Divided by 2 here. Add x to both sides here is the quicker way. We get x equals 0, or 4 equals x, which means the domain violations x cannot equal 0 or 4. And you might put it as 0, 4. I don't like this one as much because people might think that's coordinates from graphing. You don't need to go through that whole thing. I was just illustrating what's going on. So pause this if you need it up a little longer. I'm going to go back to this step right here. Faster approach. A minus B over B minus A equals -1. If they change order like that, just put in it, cancel them out and put a -1 in. So x minus 4 times x minus 4 over 2x times 4 minus x. These two, top and bottom, they have the x, the 4, but the ones that are being subtracted switches. I'll cancel out them both. I'll replace one of them with a 1, replace the other one with a -1. And then I've got -1 times that, but negative times anything is just that number. So you don't need to actually multiply the -1 by -1, but I was illustrating where it comes from and why it works. So that's like maybe, I don't know, shortcut maybe? The reason you may think this is unimportant, and you're like, where will I use this? These concepts show up a lot in calculus. We might have something like x squared minus 4 over x minus 2. And if we factor the top, we have x minus 2, x plus 2 over x minus 2, which simplifies to x plus 2. But x minus 2 cannot equal 0, which means x cannot equal 2. And then what we'll do in calculus you'll explore what happens to this ratio or to this rational expression as x gets close to or approaches. That's the word they like to use in it. X approaches 2. So what happens, and they often do it like this, what happens as x, and they'll do an arrow for approaches, x approaches 2. So like this and this, that's what that arrow means, x approaches 2. So like, and you'll do it, or you'll look at it from the left and right. From left and right. So maybe we start at x equals 1, x equals 1.9, x equals 1.9999999, keep going. Or if we do it from the other way, we could start with like x equals 3, x equals, get down to like 2.1, x equals 2.00001, something like that. We're getting close to the value of 2, but we're not at 2. And that's what you'll explore in calculus. Good stuff. Okay. But there is a reason to be comfortable with these rational expressions and canceling stuff out. Okay. So earlier I was mentioning the fundamental theorem of fractions. So recall, a over b times c over d equal, oh, this isn't the fundamental theorem. This is similar to that though. This is multiplying fractions. So here, this topic, we're going to do multiplying rational expressions. We looked at what they are. That was part objective 1. We looked at the rational expressions. Now we're going to look at multiplying. Then we'll look at dividing. And then we'll look at doing addition or subtraction of rational expressions. And so that's the multiplying. If we do the division, a over b divided by c over d. Recall when you're working with fractions, that just means flip over the fraction, second fraction, and change it to multiplication. And then this becomes one fraction. For the top one, b cannot equal 0, d cannot equal 0. And for this one, b can't equal 0. D was on bottom in the first place. D can't equal 0. And C is on the bottom here. C cannot equal 0. None of this can equal 0. And let's face it, if A is 0, this whole thing is trivial as it is anyways. And this is trivial if A equals 0. Makes the whole thing 0. Whole expression 0. But it is a valid input. But if you had A equals 0, you're not going to do anything with it. And when we did this with numbers, we did this with numbers or numerical constants. But the mathematics applies to polynomials as well. Okay. For example, six y to the sixth over 7 times 28 over 9y squared. This equals 6y to the sixth times 28 over 7 times 9y squared. And rather than multiplying the numbers together, I'm going to factor everything and cancel. Don't multiply yet. Factor and cancel like terms. So on top, 6 is 2 times 3. And I see a y squared at the bottom. I can really write y to the sixth as y squared times y to the fourth. And I'm using the bottom to help guide that decision. 28 is 7 times 4. And 4 is 2 times 2. And they're all separated by multiplication. On the bottom, 7 is prime. 9 is not, though. 9 is 3 times 3. And I've got a y squared on top. I could write it as y times y, but we'll leave it as y squared. I don't have any 2's on bottom, so the 2 is fine. Literally just go across the top or go across the bottom. There's actually less terms on bottom, so I'm going to go across the bottom and look for any like term on top and cancel it out. So I have a 7 on bottom and a 7 on top. I can cancel those out, replace them with 1s. I have 1 3 on top and 1 3 on bottom. I can cancel those out, replace them with 1s. I don't have another 3 on top, so I'll leave that one alone. And I've got a y squared on top and bottom, and I'll cancel those out, replacing them with 1s. And what we're left with is 2 times 2 times 2, y to the fourth on top, 7 times 3 on bottom. This is 8y to the fourth over 21. Okay. Oh, no, sorry, the 7 got canceled. 8y to the fourth over 3. My bad. My bad. There's another way to do this, rather than, if you don't like breaking up the y squared or the y to the sixth to y squared and y to the fourth, or factor the numbers and leave y's. So 2 times 3 times y to the sixth times 7 times 2 times 2 over 7 times 3 times y squared. Same stuff's going to cancel, a 7 and a 3. And we're going to be left with 8y to the sixth over 3y squared. And remember, we had the one exponent over the other turns into doing it as subtracting the exponents. And 6 minus 2 is 4. So 8/3 equals y to the fourth power, or 8/3 times y to the fourth power. Get the same thing either way. Note, we can have the y4 to the right of it and treat 8/3 as a coefficient or a number in front. Or we can put the y to the fourth on top, because this is effectively y to the fourth over 1. All right? Let's give you another one, a little more challenging. I want you to pause this when I'm done writing it and try factoring this and simplifying this as much as you can. So on the first expression, I've got the quantity 4n squared plus 3n minus 10. And on the bottom, I've got the quantity 2n squared plus 3n minus 2. And I'm going to multiply that by the rational expression. We'll have 2n minus 1 on top and n plus 4 on bottom. So try to simplify this. Okay, I'll assume you paused it and worked on it. Note that the right ones, these are already simplified. Already as simple as they'll get. And I actually like to do them, label them, what I'm doing when I'm doing work, because I don't want to do it all at once. I'm going to call this top part A, and I'm going to call this bottom part B. Okay? So when I factor A, the top, I've got 4n squared plus 3n minus 10. This is like ax squared plus bx plus c, or an squared, I should say, where a equals 4, b equals 3, c equals negative 10. So we'll do our trinomial factoring. A times c is 4 times negative 10 is negative 40. B equals 3. And they multiply to make a negative number, which means 1 is negative, 1 is positive. They add to a positive number, so the bigger one's got to be positive. So negative 1 times 40, that adds up to 39. I'm quite a ways away from it. I'm going to jump to, let's try negative 4 times 10. That's 6. Astro, quiet. And we're getting close. We're almost at b equals 3. Let's try 40 is 8 times 5. So let's do negative 5 times 8. That adds up to 3. So those are our things. And a does not equal 1. So I really got to treat this as break up the 3n into these coefficients, negative 5n plus 8n. Astro, come. Astro, come. Come here. Astro, come. Okay, we'll do grouping. I'm going to pause the video real quick. All right, sorry about that. Walmart had a delivery, and if you heard the dog, that's the dog letting everyone know that something's wrong. Someone's there. He sounds like someone's torturing a cat. I know. Back to where we were. We broke up this trinomial into 4 terms. Then we do by grouping. We can factor an n out here, and we get 4n minus 5. These 8 and 10 are both divisible by 2, and that leaves a 4n minus 5. So the top breaks down to, we've got the 4n minus 5. We can pull that out, and that leaves behind n plus 2. So that's my top. I'm going to throw a box around it because I'm going to come back and find it later. And I'll leave a label. That's A. Now we're going to work on B, the bottom. (2n squared plus 3n minus 2). Same process, A times C. 2 times negative 2 is negative 4. B equals 3. And there's only so many combinations that make 4. And we've got -1 times 4, you got -2 times 2, and you got -4 times 1. The only one that works is the one on top. -1 times 4 equals 3. So we'll do the same thing again. We'll split that 3n up. -n plus 4n minus 2. We'll do by grouping again, and n comes out in the first one. I got 2n minus 1. The second one, I can pull out a 2, and I get 2n minus 1. The 2n minus 1, I can pull it out, and that leaves behind an n plus 2. And that's my bottom, that's B. And so now what I'm going to do is I'm going to go back up to the top and replace those 2 trinomials with what I had. So the top becomes this one. I've got 4n minus 5 times n plus 2. And the bottom is 2n minus 1 times n plus 2. And I'm multiplying by 2n minus 1 over n plus 4. And we can try to cancel. It looks like an n plus 2 cancels from top and bottom, leaving behind a 1. 2n minus 1s cancel, leave behind a 1. This simplifies to 4n minus 5 over n plus 4, with all of these original terms on bottom can't equal 0. 2n minus 1 cannot equal 0. N plus 2 cannot equal 0. N plus 4 cannot equal 0. Okay. That was a multiplication one. Let's do a division one. We've got 5x squared minus 16x plus 3 over x squared plus x minus 12 divided by 30x squared minus 6x over 2x cubed plus 8x squared. And before I get you started, my pro tip, Jones's pro tip, flip the second fraction and change to multiplication first. And change to multiplication first. Change to multiply before factoring. That's what I mean by first, before factoring. All right. So, flip it. Flip it. Oop, there's an x in there. Minus 16x plus 3 over x squared plus x minus 12. The divided sign turns into multiplication when I flip the second fraction. I'm off the screen. There we go. So pause the video right now, factor everything, cancel what you can, see what you come up with. Pause the video while you do. I'll assume you paused. I'm going to label them A, B, C, and D. A, 5x squared minus 16x plus 3. If you go through and cancel it or factor it, you should get 5x minus 1 times x plus 3. That's not right. X minus 3. Something's not right here. What did I do? Yeah, minus 3. Yeah. B, x squared plus x minus 12. That turns into 12 will be 4 and 3. We want the 4 to be positive. C, I can factor out a 2x squared. 2x squared comes out, and it leaves behind an x plus 4. And then the D, they both have a 6x in them. Leaves behind a 5x minus 1. And so now I'll reassemble. I put A on top. I've got 5x minus 1 times x minus 3. On the bottom, I've got x plus 4, x minus 3. C is 2x squared times x plus 4. If you want, you can put the 2x squared in parentheses. And bottom is 6x. You can put that in parentheses if you want. It's not necessary. Good idea, though, when you're canceling. I'm going to make a note real quick. This tells me x plus 4 does not equal 0, so x does not equal negative 4. That tells me x minus 3 cannot equal 0, so x can't equal 3. 6x cannot equal 0, so x cannot equal 0. And 5x minus 1 cannot equal 0, so x cannot equal 1/5. Those are all bad juju numbers. Bad juju. Now I'll cancel what I can. Starting on the top, I'll just go across. I've got a 5x minus 1 on top and bottom. Those cancel and leave behind a 1. X minus 3's cancel. Those leave behind a 1. I'm going to come back to this 2x squared and the 6x because I didn't really actually factor the 6x, and I probably should have. X plus 4's cancel. Leaves behind a 1. But I wouldn't have factored the 6x or something like that first. I was just finding a greatest common factor. Notice this all trims down to, all I've got left on top is 2x squared. All that's left on bottom is 6x. 2 over 6 simplifies to 1 over 3. And we can subtract exponents. There's an invisible 1 on the exponent on the bottom. 2 minus 1. Or this all simplifies to 1/3 x, which is equal to x over 3. Either one works. Okay. And then they'll make it even hairier. So let's do a even worse one. Let's throw some of your special factoring in. Let's do x squared minus 1 over x cubed minus 1. And we're going to multiply that by xy minus 2y plus 3x minus 6. That'll be the top. The bottom will be xy plus 3x plus y plus 3. And try pausing this and factoring this. Okay. A, B, C, D, worth noting and going through and keeping track of what you do. This is really just organizing it, why I do that. So A, x squared minus 1, that's a difference of squares. So this will be x minus 1, x plus 1. B is a difference of cubes. And I haven't rewritten that one down. As a reminder, a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. So I'll do that here. My x is the a, my b is the 1, so I'll have x minus 1. And then a squared will be x squared. So a minus b. And then I want a squared plus ab plus b squared. So a is x, x squared. A is x, b is 1, so x times 1 is just x, and b squared is 1 squared is 1. So that's one thing, that's A, that's B. Take a look at C. xy minus 2y plus 3x minus 6. I've got 4 things. I'm going to try to group them together. 2 of them have y's, so I'm going to try to work with those 2 together and these 2 together. I can pull out a y here, and that'll leave behind an x minus 2. Here, there's no x's in the second term, but they're both divisible by 3. If I do that, I've got that. And notice I've got x minus 2 in both spots. I can pull that out. And it leaves behind a y and a plus 3. That gets its own parentheses. And that'll be C. And then we'll take a look at D. Remember, pause these videos when you need to get caught up. That's the wonderful thing about video lectures. You don't have to go like, hold on, instructor. A lot of students won't do it when they should. You should be willing to ask an instructor to slow down in class. Okay, if they're going too fast, you're not getting it, and there's a good chance you're not the only student that's not getting it. Teachers don't know when they're going too fast. I've been a little bit less worried about it because I know you can rewind and pause and do stuff like that as needed. So D, we had xy plus 3x plus y plus 3. These both have x's in them, so I'll just work with those. I'll pull out an x. That gives me a y plus 3. I kind of want what happened last time. I wanted another y plus. I want the parentheses to repeat. And it looks like it will. If I put y plus 3 down in parentheses, I can put that as times plus 1. Which means I can pull out the y plus 3. And that leaves behind an x plus 1, gets its own parentheses. That was D. So now we'll reassemble. I've got A is x minus 1, x plus 1. B, x minus 1, x squared plus x plus 1. C, x minus 2, y plus 3. And D, y plus 3, x plus 1. And we go through and cancel like terms. They both have an x minus 1 in them. I'll replace those with 1s. They both have x plus 1 in them, top and bottom. I can replace those. Y plus 3's cancel out. I can replace those. This simplifies to x minus 2 over x squared plus x plus 1. Okay? So that's doing the multiplying and dividing. Let's take a look at adding and subtracting rational expressions. And recall we had to get a common denominator. And it's true for either plus or if we're adding or subtracting. So if I have like A over B and I'm going to add or subtract C over D, the way to get a common denominator is just take the simplest way. It may not be, or I'm sorry, the easiest way. The easiest way is just take the other denominator and multiply top and bottom by it. So this D, I'm going to take this and I'm going to multiply this by D over D. This B, I'm going to take this one, I'm going to multiply this one by B over B. If I do that, I get, and I'm going to put them in alphabetical order here. I get AD on top, BD on bottom, plus or minus BC on top, BD on bottom. And when we add or subtract fractions, the bottom does not change when you have a common denominator. You only add or subtract the numerator. So this might have been a while since you did this, so let's just start an example with numbers. Like let's say we've got 1/4 plus 1/5. I'm going to take the 5 here, multiply the 1/4 by 5 over 5. The reason why we can do that, 5 over 5 equals 1. So I'm multiplying by 1, and multiplying by 1 doesn't change anything. That was the whole identity property. Identity property. So those weird named properties that we used earlier, that's why they bring them up, because we use them a lot. We just don't use the terms when we're doing it. Here I'll use the 4, I'll multiply by 4 over 4. And now we multiply numerators and denominators separately. This is 5 times 1 over 5 times 4. I'm just going slowly to show you what we're doing. Normally I would have just done the 5 times 1 right away. So this is 5 over 20 plus 4 over 20, which is 5 plus 4 over 20. We do not add the 20s. Do not add the 20s, just the numerators. This ends up simplifying to 9 over, or adding up to 9 over 20. You should try simplifying. 9 is 3 times 3, and 20 is 4 times 5, which is 2 times 2 times 5. Nothing cancels. So 9 over 20 is as simple as it gets. Okay. Now, if you don't want to multiply by that, the denominators directly across, let's take a look at another one that's got variables in it. So let's look at 3 over 10x to the 4th plus 2 over 15x squared. An easier way to do this, rather than, because if I multiply by 15x squared and 10x to the 4th, I'm going to have to simplify later on. It saves some work if you just simplify in the beginning. Well, it might. 10x to the 4th is 2 times 5 times x squared times x squared. And I'm using the x squared down here to guide it. 15x squared is 3 times 5. So I'll have a 5 here. I'll put a 3 over in a new column. And then I've got an x squared. The least common denominator, LCD, in this form is every column. 2 times 5 times x squared times x squared times 3. 2 times 5 is 10, times 3 is 30. X squared times x squared is x to the 4th. I can rewrite these as something over 30x to the 4th. And if you do this little table like I did, the holes in the graph will show you what to multiply each fraction by. Okay. So what do I mean by that? What are the holes in the graph? Look at the rows. 10x to the 4th has a hole here. It's empty there. And that column is a 3. So I'm going to multiply this by 3 over 3. The whole equals 3. In this column, this row, what does the whole equal? It's missing a 2, and it's missing an x squared. The whole for the right hand thing is 2x squared, which means I'll multiply this one by 2x squared over 2x squared. Okay. That's doing the table format. It's similar to how I did the greatest common factor earlier. Greatest common factor, we use completely filled columns. Here, the LCD, and as a reminder, LCD is least common denominator. You might have also heard lowest common denominator, same thing. Lowest tends to mean elevation now. It has more than one meaning. Least references a quantity only. So it's less ambiguous. Least common denominator. So if I do that, notice 3 times 3, I'll fill that in. I'll write it there. But notice 3 times 10x to the 4th does give me 30x to the 4th. And I've got the 2x squared times 2 on top here. Notice if I multiply 2 and 15, I get 30, and x squared times x squared equals x to the 4th. So that the whole using the whole method does work. If you do this table, columns have to be unique. Only one value in each column, and then you follow that format. So 3 times 3 is 9. And 2x squared times 2 is 4x squared. And I got 30x to the 4th. I can put them together, and I get 9 plus 4x squared over 30x to the 4th. Even if I try to treat this top thing as 2 squares, it's added. And we don't, remember, we couldn't factor the sum of squares. So the top does not simplify. There's nothing we can do with it. And so that's our answer. So since I wrote a lot, I'll re-show what we started with. 3 over 10x to the 4th plus 2 over 15x squared equals 9 plus 4x squared on top, 30x to the 4th on bottom. What did we do? Find LCD, multiply each rational expression so that we have a common denominator. Two, combine fractions. And recall, we're going to only either add or subtract top, not bottom. Once you've done that, try to simplify. The top doesn't factor, so it's going to be simplified. All right, let me give you guys one to try. You try. Let's do 4 over 12x cubed plus, and notice I'm putting a space in there so that I have room to write in front of it later on. There's my pro tip. Pro tip, leave space to put your multiplier. And use the table to find holes. All right, I'm going to assume you paused it and you did this. We got 12x squared, 18x cubed. 12 is 3 times 4, which is 3 times 2 times 2. I'm going to do the 18 next so that I can keep my numbers all together. I didn't like having that 3 at the end in the last table. I didn't like that. So I'm going to do all the numbers first. 18 is 3 times 6, and 6 is 2 times 3. I got a column for a 2, but I need another 3. And if you want, you can do all the x's out. There's 2 on top and 3 on bottom. My LCD is 1 from each column. This is 6 and 6, so 6 times 6 times x cubed, 36x cubed. I should end up with 36x cubed on the bottom of each. And the 12, the whole for the 12x squared is missing a 3, and it's missing the x. So I'm going to use that, and we'll do 3x times 3x. So I've got 3x times 4 here. And the 18x cubed is only missing a 2. I did this the other way around. What am I doing? I screwed this up. This was x cubed. This was x squared. That makes the x up there, and this was the whole down here. So that didn't have an x. That just had a 3. Sorry. Went too fast. This one's got the 2 and the x. There we go. So we'll multiply this one by 2x over 2x. 2x times 3. All right. Notice if I had 3x and I checked the multiplication, 3x times 12x cubed would have given me x to the 4th. That would have told me I'd done it wrong. Here we put the fractions together, and I'll do the multiplication. 3x times 4 is 12x, and 2x times 3 is 6x. Where am I? I don't have an x there. I did it again. No x there. 3 times 4. There we go. 12. So I've got 12 plus 6x over 36x cubed. It looks like the top I can factor out a 6, right? This becomes 2 plus x. And if I treat that 36, I've already factored the 36, so you don't have to do it again. Notice I've got a 6 times 6. So if you've already got the LCD factored out, you don't have to redo it. Just take the row that you had there and use what you need. I need a 6. So this is 6 times 6, x cubed. And one of the 6's will cancel. And I'm left with 2 plus x, which is the same thing as x plus 2 over 6x cubed. So I'll write what I said there. You don't need to refactor this. This when simplifying, if you made the table. The factors are the LCD row. Okay. We're almost done. Couple more ideas. So let's say we've got 7m minus 5 over or plus 2m times 5 or over 5 minus m, not times, divided by 5 minus m. We have a denominators that look similar. Remember, these two are opposite. So what I can do is I can make this 7m minus 5 and make this plus, I'll put a negative on it. I still got 2m on top, but that makes the bottom m minus 5 because 5 minus m equals -1 times m minus 5. So I'm taking that, I'm replacing it there, and I just put the -1 out front. When you got a -1, it just makes a negative sign. Now I've got a common denominator. I can put them together. I've got 7 plus a -2m, which is the same thing as 7 minus 2m over m minus 5. And both of those are already simplified, so that's your final answer. So far, the denominators have been single terms, but they don't have to be. Let's do 4 over x minus 3, x plus 5. And then I'll leave some space to write if I need to. 6 over x plus 5, x minus 5. That black pen's dead, throw it away, get a new one. I got 2 jars of pins here. I got like 40 pins here, so I don't run out. So what are these are actually a lot easier to do. So I've got x minus 3, x plus 5, and I got x plus 5, x minus 5. If I do the table, the top is already factored. The bottom, I'll line up what I have. I got an x plus 5 already. I'll line that up with that one. I'll make a new column for x minus 5. So my LCD is 1 from each column. X minus 3, x plus 5, x minus 5. The holes tell me what to multiply. The top row is missing an x minus 5. So I'll multiply this by x minus 5 over x minus 5. And the bottom row is missing the x minus 3. So we'll multiply this by x minus 3 over x minus 3. You can write the next, like in the last couple problems, I wrote the next step just by putting or showing the 2 things written out, what they are. But we can skip it, fast forward. We got 4 times x minus 5 here. And I've got minus 6 times x minus 3 here. You really want to multiply this out and combine like terms on top. So if we do that, equals, bottom is still the same. Four times x is 4x. 4 times -5 is -20. -6 times x is -6x. -6 times -3 is plus 18. Combining like terms, 4x minus 6x is -2x. -20 plus 18 is -2. The bottom is still x minus 3, x plus 5, x minus 5. The top does factor. I can pull out a -2 and have x plus 1. left behind. But nothing cancels. I'm not sure which one MATLAB is going to take. This is the fully factored one. So if they want you to fully factor it, that's the fully factored one. Nothing cancels though, so I wouldn't even multiply this denominator out. Why? Unless it asks you to, unless it says remove the multiplication or something like that, this is the best form. Okay? All right. Next thing we're going to do is more complicated fractions. So complex fractions, that's what they're called, don't have complex numbers in them. They have fractions within fractions. Or if you ever saw the movie, it's kind of like fraction inception. You ever saw the movie Inception? That had a dream world within a dream world. So let's give an example, and that'll help motivate some ideas how to do it. So my first example is going to be, we're going to start with 3 plus 4 over x squared. And then I'm going to have 6 minus 1 over x squared. And some approaches work better than others if the denominator is simple. So one approach is the following. Find the LCD of the inner fractions, or smaller fractions. And multiply everything on top and bottom by it. All terms by it. So I'll give you a second to write that down. What is our least common denominator for our inner fractions? Well, the only one with fractions we got have x squared on bottom, so it's x squared. So I'm going to take x squared, I'm going to multiply everything by it, which means distributing it like that. And if I do that on top, 3 times x squared is 3x squared. And on the second one, I've got the x squareds cancel out, but I'll show that. I'll do a sub-step first, just to illustrate it. On bottom, 6 times x squared is 6x squared. And then 1 over x squared times x squared is x squared over x squared. And this shows why we multiplied by that LCD. If we do that, notice the x squareds on top cancel, leaving behind a 1, and that just becomes a plus 4. X squareds cancel on bottom on that term, leaving behind a 1. 1 divided by 1 is 1. Okay? And that's our answer. 3x squared plus 4 doesn't simplify, so it doesn't matter whether the bottom does or not. That's good. And if you're ready for our final one, our final example has something similar. Let's take a look at 1 over y plus 1 minus 1 over y minus 1 all over 1 over y plus 1 over y plus 1. What's my LCD here? I've got, well, let's just list the denominators. I've got y plus 1. I've got y minus 1. I've got a y, and then I've got another y plus 1. Terms have to are not separated by addition or subtraction. So y plus 1 is the whole term, which means y minus 1 is its whole term. We'll make a new column for it. Y is the whole term there. And I've already got a y plus 1, so I can do that. And my LCD is 1 from each column. Y plus 1 times y minus 1 times y. So this is the other approach, just get a common denominator. I'm going to multiply this by the y plus 1 is missing a y minus 1 and a y. So I'll multiply by this by y and y minus 1 over y and y minus 1. The y minus 1 is missing the y plus 1 and a y. So this is y times y plus 1, y times y plus 1. The 1 over y is missing both the plus 1 and minus 1 version. And the y plus 1 is missing the y minus 1 and the y. So, big fraction bar. Where's my black pen? There it is. In each case, I've got y, y minus 1, y plus 1. For all of the inner fraction denominators. And now I'll look what happens. If I take the y and y minus 1 and multiply it here, I get y times y minus 1 there. There's a minus sign between them. And there's a plus sign down here. Here, 1 times y and y plus 1 is that. Down here, I've got y plus 1 times y minus 1. And here, I've got y times y minus 1. Okay. Then I've got, let's just put the top and bottom together. Y times y minus 1 minus y times y plus 1 all over that LCD. Rather than rewrite it, I'm going to write LCD. And on the bottom, I've got y plus 1 minus y minus 1 plus y times y minus 1. And that's all over an LCD. And I'm dividing fractions here. Dividing fractions is the same thing as multiplying the reciprocal. So pause that if you need it up longer. I'll try to leave that up where we can access it. So this is the last part we ended on right there. I'm going to rewrite this as the upper fraction multiplied by the reciprocal of the bottom fraction. So I've got y times y minus 1 minus y times y plus 1 over the LCD. And then I multiply by, flip this one. That puts the LCD on top. And I've got y plus 1, y minus 1, plus y times y minus 1 on bottom. LCDs cancel. Okay? We could distribute. Y times y is y squared. Y times -1 is -y. And I got negative y times y is negative y squared. Negative y times 1 is negative y. On bottom, y plus 1 times y minus 1. That's the difference of squared formula. That's y squared minus 1. And then I've got plus y times y is y squared, and y times -1 is negative y. And we'll cancel out any like terms we have. Look, y squareds go away, and I can add those two together. This equals -2y. The bottom, we can put the y squareds together. We get 2y squared minus y minus 1. Okay? Did I do that right? Plus y squared minus y. Yeah, okay. All right, so this is a little bit long, getting that whole big complex fraction. Shortcut. Multiply all things by the LCD. So let's go back to that 1 over y. And the LCD was y plus 1, y minus 1. You still got to find the LCD. If we multiply through by it, the last one, I was really doing the last part just to show you why it works, why everything's working. I can cross off the y plus 1s, and it leaves y times y minus 1 on top. And here I got a minus. The y minus 1s cancel, and I'm left with y times y plus 1 on top there. On bottom, the y's cancel, and I have y plus 1 times y minus 1 there. And here, the y's plus 1s cancel, and I'm left with y and y minus 1, and there's a plus sign. So I started with the black part, the complex fraction, multiply by the LCD. It shortcuts, it cancels you, gets you right to there. Notice on the previous page, I got a common denominator, then I had to rewrite it as flipping the fraction and canceling what I could, putting it together. It's easier just to multiply by the LCD. I thought I would show you both ways, depending on which one you like. One of them is more work, they get to the same spot. But that's what it is. That's chapter R5. There's plenty of practice if you need. Come on Zoom for online classes, or ask me in my office hours for a regular semester. After class, come on up after class. All right, that's the end of the video. Peace.